Hi, college algebra kids. I hope you were able to watch our first video on section 4.1. This is our second video. It's 4.2. This is over logarithmic functions. Remember, these blank packets and the completed packets with all of my notes on them, those are all under content on Blackboard, so you can find them there, Unit 4, okay? Well, today we're going to be talking about section 4.2. This is all about logarithmic functions. Now, logarithmic functions are the inverse of exponential functions. And we know from math that inverse functions are the opposite, almost, if you will, function of the original. So there's definitely a relationship there between a logarithmic function and an exponential function. And we're going to focus on that today and how to go back and forth between the two of them. Now, logs, if you will, that's what we're going to call logarithmic functions for short. Logs are extremely important because they allow us to solve these exponential equations. Now, they do some other things as well, but the most important thing is that they help us solve these exponential equations. So in those, if your exponent is the variable and you're solving for that variable, you have to get it out of the exponent. And removing an exponent is really tricky. And so that's where the log comes into play. The log makes it really easy to do that. And so that's why logs are so important. And that's why we need to focus on those. So what you see here is your basic log function. We know it's a function because it says f of x. We can replace that with y. Then we see the word log, and we see an x. Those are on the same level. And then drop down below, sitting right below there next to the log as a subscript is b, and that's the base, okay? So when we want to describe what you see here, we say this is log base b of x, okay? So b is the base, x is the argument, and it's a log. Now, for log functions, your argument has to be greater than 0. Not equal to 0 and not negative, but greater than 0. And your base has to be greater than 0, and it cannot be 1. And we'll go into more details about that later on once we get past the first couple of pages of this section. Okay, then you'll notice here that we have two equivalent or the same expressions. We notice y equals log base b of x, we just replaced f of x with y, is equal to x equals b to the y. Now in both cases, b is your base. It's the base of the log function and it's the base of the exponential function. So no matter which form we're in, the base is the base. Now, this is what changes. With the log function, x is the argument, and the whole thing is set equal to y. When we change it to the exponential equation, the argument becomes what it's equal to on the outside, and the y actually becomes the exponent. So we're going to look at how to do that now. So we are going to start with the log on the left, LL, log on left. If your log is not on the left, put it on the left. Just rewrite it so that it's on the left, okay? That goes for the exponential form as well. Make sure that exponential piece is also on the left. You're going to begin with the base, and you're going to move below in a counterclockwise rotation, just like this. Okay, let's start. So I notice here for a and b, I have two log functions, and I want to rewrite those as exponentials. Okay, so that's all we have to do is rewrite them in exponential form. First thing I notice is my log is not on the left. So let's rewrite that. I'm just rewriting this over. So my log is on the left, and then the other piece, which happens to be a 2, is on the right. Okay, now I forgot to mention I made a mistake on this problem. we do not want that 6 there. So we need to correct that. Mistake on letter A. Get rid of that 6. So I'm actually just going to erase it on mine, but from the get-go, you don't even have to write it. There we go. Okay, now that we have it written, we're going to start with our base, and we're going to come around here to the 2. So we're going to write our base, which is 5, come around to the 2, that's going to be our exponent, and then we're going to do equals the argument. And there's our answer. We wrote it in exponential form. Base over the bottom to the other side, that's our exponent, equals your argument. And you can even check that in the calculator. Now I'm sure you don't have to. You know 5 squared is 25. Let's try the next one. My log is already on the left, so I don't have to do anything. I'm ready to start. I'm going to start with my base, which happens to be a y. Over to the other side's my exponent. Across the top is equal to the argument, equals 16. And there we go. That's all we had to do. And then you could even realize that actually y could be 4 or -4. Either one of those squared would give you 16. So you could even take it a step further and go ahead and solve that. But this is all that's required right now, is to write it as an exponential. So you start with the base, move under till you get to the other side, that becomes your exponent. Over the top is equals the argument. Okay, let's go the other way. Here we have 3 exponentials and we want to write them as logs, okay? So my exponential's on the left, just like I wanted. I know if I want to write a log form, I'm going to have to write the word log. Base becomes the base, so the base here is 6, the base of the log becomes 6, okay? I go underneath to the other side. That becomes the argument. Over the top is the equals, and that's going to be equals 4. And there's our answer. Okay, so I started with the base, argument, over the top is equals the 4. Every time you go over the top, it's equals whatever is left. Okay, it's whatever is left. All right, here we go. I notice that my exponential is not on the left, so I'm going to have to rewrite that first of all. So I'm going to move him to the left, and this part is going to go on the right. Okay, now I'm going to write the word log. Here's my base, it's a 5. Okay, I go underneath to this other side. That's what I write next. Over the top is equals what's left. And there we go. Now I know that was a strange one. If you want to put this argument in parentheses, you can. You don't have to. And there we go. Okay, now let's look at C for a minute. C is obviously not a log equation because there's not the word log, but it's not an exponential either because I don't have anything raised to an exponent. So we are going to have to make it into an exponential. Okay, so let's think about this for a minute. We know that a root is actually a fractional exponent. So do you remember we said that square root of, let's say, 3 is equal to 3 to the 1/2 power. Remember, the numerator is the exponent, the denominator is the index of the root. Okay, so let's say we had 3 to the 4th power and it was under a square root. We could write this as 3 to the 4th, this is a square root again, over 2. Well, that's a bad example because look, it can actually be reduced. 4 divided by 2 is 2, and that's actually 9. But this is what we want to really pay attention to, and that's the fact that you can write a root as an exponent. So let's go back to our original equation and let's rewrite this. So if I want to rewrite this problem, 8, and then what kind of an exponent would a cubed root get? Well, if a square root became 1/2, a cubed root is going to be 1/3, and that equals 2. Okay, so I just rewrote it, giving it an exponent, and now I can write it as a log expression. I have the word log. Here's my base. Underneath is a 2 equals the 1/3. I ran out of room there, but that's what we have. Okay, so we're going to use that little trick whenever we need to go from one way or the other to rewrite these things. All right, let's turn the page. We're on page 7 now. Let's look at a couple of very important logarithms. These are actually both going to be test questions, so you want to be really careful of this. All right, sometimes you will see log x. In fact, if you look at your calculators, you have a log button. Well, how do you know what the base of that is if it just says log, or if this just says log? Well, it turns out it's understood. It's kind of like when you just have a plain old root, you know, whoops, that is in fact a square root if there's no number there. If you don't see a base on a log, it just so happens that base is 10. So this is the log you see on your calculator. It is understood that it has a base of 10. If you don't see a base there, it's a 10. Okay, let's look at the next one. The next one just says ln x. So if we go back to our calculator, somewhere near your log should be an ln button. Now these are capital L's and N's. In math, you normally see lowercase l's and n's. Same thing, an ln is the natural log. The ln of x is the same thing as a regular log with a base of e. These are exactly the same thing. So that's one of the reasons why if on your calculator, when you hit second log, you see a 10, because that's its inverse. When you hit second natural log, you see an e. That's its base. So the base of a log is understood to be 10 if you don't see a specific base. The base of the natural log is understood to be e. There we go. All right, let's look at some other rules. Well, some other rules tell us that if the base and the argument are exactly the same on a log, it equals 1. If you can memorize that, then you can fly through a lot of those homework problems. Now let's look at why that would be. If we wrote this in exponential form, we would start with the base. We would come over here to 1. Over the top equals 7. And sure enough, 7 to the 1 power is 7. So that's how this works out. That's why if these two values are the same, the base and the argument, it's equal to 1. Now, if the argument is 1, no matter what the base is, we don't care what the base is, if the argument is 1, the whole thing is equal to 0. So let's look at that for a minute. If we were to rewrite this in exponential form, we would start with our base, raise it to this other side, over the top equals 1. Well, we know this is a true statement because one of our exponent rules that we learned way back when is that anything raised to the 0 power is 1. And so that's why if your argument is 1, regardless of the base, your answer is 0. Okay, let's do some little examples now. This says to complete these without using a calculator. So we really want to think about what we're doing. Now, could you use a calculator? Yes, you absolutely could. But let's just think about it and see what we can come up with. And we want to find the exact value now. All right, well, I see a log function. I'm going to set it equal to y. And I'm going to write it in exponential form because my brain works a little better like that. I just learned about logs, and so I need a little time to get accustomed to them. So let's start with our base of 4. We're going to raise it to the y power, and we're going to set it equal to 64. And now we're going to use our knowledge of math to say 4 raised to what power would give me 64? Well, 4 raised to the first is 4. 4 squared is 16. But guess what? 4 cubed is 64. And you can do that on your calculator to check, which means y is 3. And that's how we're going to do this. Okay? All right, let's try this one. This one looks a little harder. We have a fraction. We're going to set it equal to y, and we're going to make it an exponential. So we're going to take our base, we're going to raise it to this other side, equals what we see over here. Okay, now let's think about this. I see a 25, and I see a base of 5. Well, I know that 5 squared is 25. What I want to know is, how do I get 25 in the denominator? Well, again, knowledge of exponents here. How do you end up with something below the fraction bar when exponents are involved? You have a negative exponent. So, if 5 to the positive 2 is 25, 5 to the negative 2 is 1 over 25. That means y is negative 2. So that's something to keep in mind. We're going to do that sometimes. All right, we have all kinds of crazy things happening here. Let's see. Okay, we're going to leave this as a root for right now because he is in the denominator. We're going to set this equal to y. Okay, we're going to start with our base. We are going to raise it to the y power, and it's going to equal 1 over the square root of 14. Okay, we need to know what y is. Well, let's think about this a minute. How could we end up with a square root of 14 if we start with a regular 14? Well, we already saw on the page before that if you raise something to the 1/2 power, that's the same as putting it into a square root. So 14 to the 1/2 power is square root of 14. And then as we just saw in the example above, how would I get that into a denominator? I would make it negative. And then I get 1 over square root of 14. So y in this case ends up being negative 1/2. Okay, so we just need to take it one step at a time and really think about this. We know how to do this. All right, these look a little simpler. Here we go. We're going to set this equal to y. We're going to start with the base. We're going to raise it to the y power equals 2. Okay. So how do I go from a 4 to a 2 using an exponent? Now don't say divide by 2 because I can't do that. I have an exponent. Well, the secret lies in our good old square root because it just so happens the square root of 4 is 2. So how would I indicate I want to take the square root? You would put, and again, I'm just going to write this over here, you would make this 4 to the 1/2 power is square root of 4, which equals 2. So in this case, y is going to be positive 1/2. I didn't want it that 2 in the denominator, so I didn't make it the negative. I just left it as a positive 1/2 here. Okay, and then what about this guy here? Log base 6 of 1. Well, just so happens I don't have to do anything because my answer is 0. Remember, if your argument is 1, your answer is always 0. Now, if we forgot that little rule and we needed a little help, we could have set it equal to y. We could have taken our base, raised it to the y power, equals 1. How do you get anything to equal 1 with an exponent? you make your exponent 0. But you could also have just automatically put 0 if you remembered the rule. Okay? All right, let's look at the rest. I know we have a lot of these, but they go really fast. Okay, here we go. F, I have log of 10. Well, I don't see a base. Remember what we learned on the page before. If you see a log without a base, what you actually have is a base of 10. So if I write this over with a base of 10, then I notice that my base and my argument are exactly the same. And one of the rules we just learned is that when that occurs, it equals 1. So you're done. Now, if you wanted to and you wanted to set this equal to y, you could write your base, raise it to the y power, equals 10, and then you would also see that from that way, y equals 1. Okay, let's go to our next one. We have log of 10 to the 5th. Again, I do not see a base, which means my base is 10. Okay, now here's an interesting little trick. We haven't learned this before, but you're gonna really like it. It's gonna come in handy. All right, the base of the log and the argument are the same, except I have this pesky exponent hanging around. Well, guess what your answer is gonna be? The pesky exponent. You can almost think of it as these canceling and leaving you with this. Now, if you need a little better explanation than that, let's pretend we set it equal to y. We would have a base of 10 raised to the y equals the whole argument, 10 to the 5th. Well, if the 10s are the same, y is going to equal 5. And there we go. Okay. All right, let's try it again here. Let's see. Here again, no specific base given, so we know it's actually a 10. There we go. Okay. Now, let's write this over a little bit because, gosh, if I could turn this 1/10 into actually 10 raised to an exponent, that sure would be handy because then I could use one of those little rules. Well, on the page before, we talked about the fact that if you want something in the denominator, if you want it to move below a fraction bar, then you can raise it to a negative exponent. Okay, so it just so happens I could rewrite this as log base 10, 10 to the negative 1 power. 10 to the negative 1 power is the same as 1/10. Same thing. Now, the base is the same as the argument. Remember, it's almost like these cancel, and what are you left with? -1. There you go. Now again, you could have done this a little bit harder way. You could have taken your base, raised it to the y equals 1/10. And then from there, hopefully you could have seen that if the y was a -1, it would have put that 10 in the denominator. Okay, now I see for I've started in with some natural logs. So remember, his base, even though it's not there, is actually an e. It's understood to be an e. And we know whether it's the word log or the natural log, if the base and the exponent are the same, our answer is 1. Okay, let's try this one. I see a natural log. I know my base is e. My argument happens to be e squared. Same situation I had up here. If my base and my argument are the same, all I'm going to do is take that exponent. And there's my answer. Okay. Well, now we definitely have a little trickiness I'm going to talk about with K and L. Look at this. Now we have a log expression that is the exponent. Well, we've never seen anything like that before. Well, let's look a little bit closer. The base of the exponent and the base of the log are exactly the same. So in that case, all you're going to be left with is that argument, 3x. The bases cancel. And leave just the argument. Oops, I ran out of room. And leave just the argument. Okay, let's take a peek at this one. Well, I don't have a base here. Well, we know we actually do, right? We know if there's no base, it's actually a 10. So when I rewrite that, I see that the base of the exponential and the base of the log are the same, which means all I'm going to be left with is the argument, the y. So a lot of little tricks there, a lot of things to remember, a lot of things to look out for. My math lab will help you work on those. So I had mentioned before that if you wanted to put some of these in a calculator, now obviously you couldn't have done all of them, especially not K and L, but some of these you could have. How would we have done that? Well, some calculators actually have this really fantastic button that allows you to put in any base you want. Normally, this only occurs in TI 84 plus and TI 92s, okay? And maybe some 89s, okay? But you have to have the plus on there, usually. If your calculator does not do that, then that's okay. We have a rule for you that we can do. Okay, first though, let's look at what if you do have this button. Well, let's look on this calculator here. Obviously, we don't see that button. We see a regular old log, and that is not the button we want. This button is only for base 10. So if we want to find this button, he's hidden. You have to go to alpha. So I'm going to write that down. Alpha. Okay. And then you're going to go to window, and it's going to be number 5. Okay, so alpha, here's window, it's up here in your graph button, window, and you go down here to number 5. Look, this was a whole hidden thing you didn't know about, and it says log base. And if I click that, look what pops up. I can put in any base I want along with any argument that I want. So in that case, I could have done, I could have gone back to letter A on the page before. We had a log of base 4 of 64. Just kind of have to keep moving this little button over, and there was our answer. Okay, so let's try that one more time. I did alpha, window, and I go down here to number 5 and I hit enter. Then I put my base in. When you're done with your base, you move your arrow over. I put my argument in. When you're done with that, you move your arrow over and you hit enter. And it was a 3. Now, again, don't worry if you don't have this button. I'm going to show you how to do it anyway on your calculator. Okay, so let's pretend we don't have that button. All right, we'll move the calculator over here. We're going to pretend we don't have that button. Okay, so here's the change of base rule. If this is what we have log base 2 of 16, and this is what we want to put in our calculator. Okay, well, what we're going to do is split it up. We're going to take the log of 16, that's the argument, over the log of 2, that's our base. So that's our plain old log button. Okay, so if you can't find this button the way that I showed you before, don't worry. Take plain old log of 16, hit enter, divided by plain old log of 2. And look at there. You get 4. And if we wanted to check this, we would take our base of 2, raise it to the 4th, equals 16, and absolutely that's correct, because 2 to the 4th is 16. And there we go. Okay, let's try this one over here. What if we move this over? Okay, we have log base 3 of 27. If we have this little tricky button up here, then you're good to go. If you don't, here's what we're going to do. We're going to take plain old log of 27, it's our numerator, over plain old log of 3. So log of 27, enter, divided by log of 3, enter. And sure enough, it's 3. So start with my base, raise it to the other side, equals 27. And we also know that 3 to the third power is in fact 27. And there we go. Okay, so that's how we're going to handle those change of base equations. Anytime we need to, you can use that anytime on MyMathLab. Even if it tells you not to use a calculator, you're welcome to do that. That's still a skill, is being able to do it in your calculator. So that's okay with me. Just make sure you know how to get the answer. Make sure you practice. Okay. All right. So let's go on and look at, I just realized my paper's off there a little bit. Sorry about that. It's Alpha Window 5. Okay, let's go over here. So next example, write the equation in its equivalent exponential form. Well, we can do that. And then solve for x. Okay, well, we've never had to do anything other than write it in the other form. This time we're going to have to keep going after we have written. So here we go. I notice my argument is actually a little parenthesis with some things happening in it, so keep that together. All right, I'm going to start with my base. I'm going to raise it to the other side, and it's going to equal that whole argument. Now, I don't need those parentheses anymore because there's nothing else over there on the right. Okay, now it's not enough to stop here. I have to keep going. So in my calculator, if I do 3 to the 4th, I realize that's the same as 81. I'm supposed to be solving for x, so I'm going to add 3. And I get 84 equals x. And that's my answer. Okay, let's try this one. Okay, I'm going to start with my base. I'm going to raise it to the other side, equals an argument. Okay, well now we have a negative exponent. I'm going to move this over here just so we can see it a little better. Okay, so now we have a negative exponent, so that means we're going to have a fraction. Well, we know 3 to the positive 4 is 81, which means 3 to the negative 4 is 1 over 81. Which equals x. And there we go. And that's the answer to that. Okay, well, let's keep going. We have a few more examples here. We did most of it, but we want to make sure we're comfortable with everything. Okay, let's look at example C. Okay, so example C, same directions. Okay, now this time, if you notice back here, we had equal signs. We don't have equal signs anymore. So in order to solve these, we may need to put in some equal signs. All right, well, first thing I notice is that we have the log of a log. Okay, so we have to follow order of operations. We have to do what's in parentheses first. Now, I know we had parentheses down here, right? But there wasn't anything we could do in there. There was no simplifying that could be done. So now that we've switched over to here, there is some simplifying that we need to handle. We need to handle this that you see right here. So we're going to do this piece first. All right, I'm going to write it over. I need to know if that is a number, because chances are it is. If you have the alpha window number 5 in your calculator, if you have a fancy graphing calculator, you're going to know that's automatically the number 4. If you don't, we're going to use a change of base. So we're going to do log of 81 over log of 3. Okay, so I get my calculator. I'm going to do plain log of 81 divided by plain log of 3. Look at there, it's a 4. I also could have done alpha, window, number 5, base of 3, argument at 81. Either way, got the same answer. Okay, so we know that is actually 4. So I'm going to put this in as a 4. Okay, so I'm going to have log base 2 of 4. So I'm going to take this over to here. Okay, and now I want to know what the answer to this is. Okay, well, again, we can go right into our calculator. I can do plain log of 4 over plain log of 2. Just so happens the answer is 2. And there we go. All right, let's try this one down here. I don't have any parentheses to worry about first, so I'm good. Okay, let's put this right in our calculator. We're going to do plain log of 1 divided by 16. You're going to need that in parentheses. I know it's not in parentheses here, but your calculator will want it. Over log of base 2. Okay, let's see what that looks like. We've got plain log of 1 divided by 16. Put that right into parentheses. Divided by log of 2. There we go. It's a -4. And there's our answer. All right, let's try another one here. Okay. All right, well, gosh, this looks a little suspicious. I have a base of 7 and my argument also contains a 7. So before I run off and start worrying about that change of base rule, let's see if I can rewrite this. I have log of base 7 and my argument is 7 to the 1/2 power, because we know 7 to the 1/2 is the same as the square root of 7. Now, since my base and my argument are the same, my answer is simply going to be my exponent. Now, could you have put this in your calculator? Sure, let's do that, just so that you can see you could have done that. I could have done plain old log of the square root of 7 divided by plain old log of 7. Now, of course, it comes out as 0.5, but you know that's 1/2. And there we go. Okay, let's talk a little bit about the argument. So we already know the argument is right there next to the base. It's on the same level as the word log. Let's talk about why sometimes things are in parentheses and sometimes they're not. Okay, well, if there is only one term in the argument, parentheses are optional. Okay, but know that the parentheses only identify the argument. They do, here's another mistake, folks, they do not, this word should be not, mean multiplication. Okay, they do not mean multiplication. So log base b of x is the same as log base b of x with parentheses. These parentheses do not mean multiplication. It just is identifying the argument and keeping it all together nicely. But since there's only one term, it's really optional whether you use that or not. This is the important part. If there is more than one term in the argument, like there's addition or subtraction there, then the parentheses are required. So this is the part where if we were in class together, I would say eyeballs, I need everybody's eyeballs, okay? Because let's look at these two different logs. Very, very, very different answers, okay? Here, what is my argument? Well, it's everything in parentheses. So it's x plus 1. Okay, be careful. What's the argument here? It's just x. And plus 1 is added in the back. That is so tricky. Please, please, please make sure that you are taking note of that, okay? So, also, you cannot touch the argument unless you use a logarithmic property, which is coming up in our next section. So don't get crazy with the canceling. I know you guys are canceling fools. If you see this, okay, so 7x is the argument here. You cannot cancel out the 7. This is already simplified. Already simplified. You cannot cancel out a 7 there because you can't break into the argument. Okay, same thing here. I have the ln, the natural log of 3x, divided by the natural log of 4x. The natural logs don't cancel. The x's don't cancel. This is already simplified. There isn't anything I can do. Now, we are going to learn about a special logarithmic property that you can use to simplify, but no canceling, no crazy canceling, okay? All right, 2 more pages. Okay, here we go. Let's talk about some graphs. So we spent quite a bit of time on exponential graphs, okay? So now let's talk about graphs of logarithmic functions. Now, we already mentioned that they're inverses. So we already know that means that there's this imaginary line y equals x here that an inverse reflects over. So for the exponential, when b was greater than 1, we looked like this, right? So, and we had a y-intercept at 1. Well, guess what? For a logarithmic function, log base b of x, where your base is greater than 1, we're going to have a x-intercept of 1. And we're going to have a vertical asymptote rather than the horizontal one. Okay, when b is a fraction, again, we're going to have, this was an increasing graph, we're going to have a decreasing graph. We're going to have an x-intercept of 1, and we're going to have a vertical asymptote at y equals 0. And so this is what we end up with there. So no y-intercepts, just x-intercepts of 1, and no horizontal asymptotes, just a vertical asymptote. Okay, so let's go over some of these information. So remember, with our exponential functions, our domain was all real numbers. Well, as you would expect, now our domain is something else, but our range is all real numbers, because remember, the domain and the range switch when it comes to inverses. Our domain is going to be 0, okay, because we're positive, to infinity, all right? If we have been translated or transformed in some way, here's how you find your domain. Set the argument greater than 0 and solve for x. This is extremely important. This is a test question, okay? If b is greater than 1, we're increasing. If b is a little fraction, we're decreasing. No y-intercept, we do have an x-intercept, and we have a vertical asymptote on the y-axis, which is x equals 0. Okay, let's match these just like we did with our exponential functions, okay? So if we scan along here to try to find our original parent function, here it is. This is our original parent function, okay? Log base 7 of x. All right, now since our base is greater than 1, this is what we should look like. Now it's going to be a little different because our base is 7, okay? But we are looking for an x-intercept of 1, and we're looking for an asymptote at x equals 0. And here we go. Here's an x-intercept of 1 and an asymptote at x equals 0. There's our original parent function. Okay, so now let's go back to the beginning and see what was changed. So if we're comparing with our original, I see that x has a -1 next to it. Okay, so don't forget, our hippos seem really violent. This is a horizontal translation, and since it's -1, that means right 1. So here we go, but I'm going to be moving over 1, so I'm going to end up with an x-intercept here at 2. So if I scan my numbers looking for an x-intercept at 2, that looks like number 51. So here is log base 7 of x minus 1. Okay, now let's look at this next one. This one's written really strangely. This one has a 1 in the very, very front. We need to rewrite him because we are not used to looking at expressions like him or functions like him. What we're going to do is keep that negative. That means there's a reflection. And then this 1 is positive, so we're going to add him to the back. And when we rearrange him the way that we are used to seeing him, I see a reflection over the x-axis and a vertical translation of 1 up. So I'm going to reflect over the x-axis because that negative's out in front, and I'm going to go up 1. So if this was my original and I'm going to reflect over the x-axis, that means that this little portion that's moving to infinity is now going to be down below. Okay, so I'm going to flip it down below. All right. So now I look like this, right? This is negative log base 7x. Okay. Then I'm going to go up 1. So then I'm scooting up 1. Okay. So in that case, I'm going to be right here at 47 because now I'm scooting up 1 little part. So if I rewrite it, I'll just rewrite it exactly the way that it was written. There we go. I've been flipped and then I've been scooted up 1. Okay. All right. So now if I go to my next one, here's my parent function, and I'm going to go down 1. So I'm looking at this guy, but I'm moving down 1. That looks just like this one. Just move down. Okay, when I look at capital F of x, he looks like this intermediate step that we had right here when we were looking at capital H of x. And so in this case, all he has done is been reflected across the x-axis. So if I'm looking for this particular picture, there we go, it's 50. 50 looks better than what I drew. There we go. And then last but not least, we have this little guy here. And the only thing different from the original parent function is he has also been reflected. I notice that that negative is on the x, which means he has been reflected about the y-axis. So here's our original. Original's going off this direction. So if we are reflecting across y, we're going the other direction, and that's how we end up pointing this way. And so here we are looking for log base 7 of negative x. And there we have it. Okay. I believe this is our last page. It is, and look, it's short. There's only 2 little examples on it. I know you've been here a long time. This is our longest section. All right, here we go. The very last thing we want to do is find the domain. And I already pointed out on the other page that to find the domain, you set the argument greater than 0, solve for x. So we're going to find our argument. Here it is. It's in parentheses in this case. Do we care about the base? No, don't care about the base at all. We're going to take our argument, set it greater than 0, and solve. Okay, well, I'm going to add 4. There we go. I want to write using interval notation, and because it's just greater than 0, not greater than or equal to, parentheses only. So what does x greater than 4 look like in interval notation? It looks like 4 to infinity. So let's also make a note here that the base does not matter when we're finding the argument. All right, let's try the next one. Okay, just for fun, what is the base? I don't even see it. Well, it's 10, right? But we don't care. Okay, we're going to take our argument. We're going to set it greater than 0. Okay, we have a little work to do here. Now remember, you want to leave your letter on the left with inequalities, so I'm not going to add x, I'm going to subtract 6. Okay, now I want to divide by 1. What happens when I divide by a negative? Your inequality sign flips, right? Flip that inequality sign, and this is a positive 6. Now, make sure you notice that I flipped my inequality. All right, parentheses, we want x is less than 6. So if I write that in interval notation,